Hey folks, welcome back. In today's session, we're going to be having a look at how we can bring animation data into Blender and work on it with simulation nodes to create this cool effect of a person dancing and scattering points off them. There's a bunch of controls and there's a bunch of little fun things to learn about using animation data with simulation nodes. But first of all, how do we get animation data? Today's video is kindly brought to you by Rokoko. They've got a new tool called Rokoko Video, which takes video data and using AI will turn this into properly motion capture data. Now, there are some definite limitations, but I'm going to talk you through a few of the processes just to try and optimize your videos and get the best results. Let's jump in. We're going to be working with Rokoko Video and Rokoko Studio today. This is a sort of two-part solution. The first part is a free online video to motion capture tool, and the second part is a free local motion capture to export it to whatever software you want. So for today, we don't need to worry too much about all of the additional tools in Rokoko Studio because we're not going to be working with full motion capture suits or gloves or facial tracking, which is other things that they provide hardware for. Have a look down in the description for the links that you will need to download and access the software that we'll be using. First of all, Rokoko Video. You're going to need to sign in because this is how you transfer your video data over to Rokoko Studio is through your account. This is entirely online, entirely free. So you'll be greeted with a dashboard similar to this. Once you sign in, I've already done some experimentation, and go ahead and create a new scene in here. I'm going to be calling this one dance video. You then get the option to record using a local device, such as this camera, or using a local video file. This is the one that I would recommend. A couple of things to be aware of. Your motion capture session has a maximum limit of 10 minutes. Secondly, your maximum video file is going to be 300 megabytes. You can upload and then trim in the browser here as well. So how do you actually get your videos that are going to work? Because this is taking video data and it's using AI to track where your hands, elbows, shoulders, and all of these kind of joint positions are. And then it's going to create that into motion capture data. So I'm going to be using this one. I just grabbed this off pexels.com. So a dancer, a locked off camera, pretty much. There is some movement in the camera, but it's very minimal. And you will actually notice, this is the one I'm going to use. You will notice that there is going to be some sliding in the motion capture data, and that is because of the camera movements. She's not super high contrast, but it is enough contrast against that flat background for the motion capture to actually track properly the different joint positions. So go ahead, download this video, or feel free to use whatever you want, or record your own as well. And then you can upload it into Rokoko Video. Once uploaded, you will be able to trim to a specific clip if you want to shorten this. Otherwise, you can rename it on the side here. So I'm going to rename this one to Dancing Woman. And you could upload additional videos as well here into this scene. Once you're ready, you can turn this into an animation and it is going to start processing. Make sure you do not close your browser window while this is happening. It takes approximately 3:1, so 3 times longer to process than the video is long. Once it's completed processing, you will see that the animation clip has been created and you can now view it in Rokoko Studio. So I'm going to go ahead over there and we can see Rokoko Studio is here. By the way, the first time you open it might take a little while as it downloads updates, but just something to be aware of there. Once it's done, you will see your recently added scenes on your homepage. Click in here and we should see a mannequin and the UI. So straight out of the box, we have a character and we have scroll to zoom, alt right click to pan around. So that's probably option on Mac. And we have right click to look around. When right clicking to look around, you can then use WASD to do your standard navigation, EQ to move up and down. So how do we actually preview our animations on here? Well, on the left hand side, we can see that in our scene, we have an object, the Rokoko Video character, which we can see here, underneath which we have animation clips. And if I double click on Dancing Woman, then I can see that the animation clip has started. And we have a bunch of things at the bottom. Let's go ahead and click play. How well is this done? Seems to have done a pretty good job. No obvious glitches. Seems to be doing pretty good. Sometimes you'll see things like legs flipping backwards and forwards or just tracking issues like that. And frankly, that is to be expected with a video to motion capture solution. That is always going to be the case when you don't have any depth information. It is assuming it from what it knows humans to be shaped like. So there's definitely going to be some errors in some video cases, but a lot of the times you can get some really good results out of it. Something that is going to be a real reason that you should be using Rokoko Video rather than one of the other alternatives, and there are other free alternatives out there, is when we can see these little discs on the feet. So you can see that these light up, and these are in line with these sections on the timeline. They're called foot locks. So the idea is that when the feet are locked, it will sort of override the motion capture data. That's not quite right, but it locks the foot, and then it uses inverse kinematics to reposition the leg, basically to prevent sliding and weird glitches. Sometimes you want it, sometimes you don't. So if you ever need to turn it off, you have this magic wand down on the left here, and we can turn off locomotion, which is going to basically no longer track the foot positions. So you can see now she's moving and sliding all over the place. So this is true to the video, but it's not doing anything intelligent with regards to the floor. So locomotion puts them on the floor, and it locks the feet when it thinks the feet are in contact with the floor. You also have toe bending, whether or not you want to do this to improve the foot articulation, that's up to you as well. So that's what these foot locks are for. Foot locks are really important with motion tracking. Just to show you an example of when you would not want foot locks and what you might be seeing in your animation that would lead you to not want them is what I've done is I've added breakdancing boy, and we can see straight off the way this leg is a bit weird. Oh, he looks like he's in a lot of pain. Right, and this is because locomotion is on. So what it's going to do is it's going to try and make sure that there is one viable foot on the floor. It can't keep it on the floor because the hips are so high, but it's also sort of tracking towards the floor. So probably not what you're after. Go ahead and just turn off locomotion, and now it's going to track where it's basically just going to track it off that motion capture data rather than trying to do anything intelligent, because you don't always want to put the feet on the floor. In this case, you especially don't. So if you want to use this kind of motion data using locomotion set to off, then it's going to give you a much better result. Now, I'm going to go ahead and export my dancing woman. So that was this one, and I'm going to keep locomotion on so that they have the foot locks. If we go over to our export panel on the right hand side here, I have a video, I have a motion clip. Now I just want to export an FBX to my software. For file format, we're going to keep with FBX. It's not the best, but FBX is a good standard. We're going to be exporting just the body mesh. I don't need a face because we don't have a face, so there's no motion tracking on that face region. There's a skeleton preset here that we're going to use is Rokoko Newton. However, if you want to use one of the others, that is fine as well. We're going to use Rokoko Newton because it's going to provide us with this model. So that is the skeleton target Newton model, and it's going to use the naming for that Newton model. And for our reference pose, this is like the start pose, and there's also a rest pose in here. We're actually not going to be exporting that reference pose, so make sure that the include reference pose is turned off. If you include the reference pose, you will get a T pose or whichever reference pose you chose for your frame 0. Can be useful, but in our case, we definitely don't want it because we're dealing with an animation that we just want to work with directly. FBX format binary is fine, the version is fine, frame rate, set this to 24. You can go higher if you want. I mean, it depends what you're after really. 24 is absolutely fine though for what we're going to do today. Everything else is off. We'll use the constant key reducer, and then you can set where you want to be saving your asset. So I'm going to be saving this, and then just go ahead and export clips. Rokoko make it really easy for us to go from having a video to having an FBX that we can work with really very little pain in between. We didn't have to get deep into Rokoko Studio, and we didn't have any options to deal with in Rokoko Video. So it is as simple as upload the video to your account, allow it time to process, and then open Rokoko Studio, check whether or not you want to turn off or on foot locomotion, and then export. So those are your steps for Rokoko. Next, let's have a look at Blender. The version of Blender we're going to use today is the experimental branch using simulation nodes from December 23rd. That is 2 months ago for me. So that's a long time for an experimental build. Some things I'm, for example, having trouble with it rendering. However, the shape of simulation nodes, and the point of this tutorial is to teach you about the processes and workflows with simulation nodes. So even though it's slightly older, and some things might be a bit more unstable about it, the shape of simulation nodes is what you can expect when we get proper simulation nodes for Blender 3.6. So it's not coming for 3.5, they're laying the groundwork for it, but for 3.6, fingers crossed, we should see simulation nodes inside Blender. If you're new to downloading experimental builds, go ahead, go up to blender.org, go to download, and scroll down to the bottom where we have experimental builds down here. Now this is going to be the like the nightly builds and things like this. We want a branch, and then you're going to go to all archive builds and navigate to the version that you're wanting. Now by the time you're doing this tutorial, there may be newer simulation nodes, so just check whether or not you can find like a geometry simulation nodes build higher up in the list. For me, I just need to go down to geometry node simulation, December 23rd, and download this. This will download as a zip file, unzip it, and then you will get access to Blender. It's like a portable install. It doesn't need to do any proper installation. It opens just as a regular install of Blender, so we are going to go ahead and import our FBX. So File, Import, FBX. Go ahead and navigate to where you saved your FBX file from Rokoko Studio. We're just going to import this with the standard FBX import options. And there we go. So the reason I really like this is because we have all of this mesh data straight out of Rokoko Studio. And there's another thing that I really like about this as well, is this is a non-deforming mesh. If I go into wireframe, these are 100% weight bones. So none of the mesh is deforming at all. It's just swinging around these mannequin joints. I'm going to make sure that my outliner has object children, just to make sure I've got my children set up nicely. And I'm also going to turn off armature view in my 3D viewport. I don't need the armature to be visible. Next, because the head is separate to the body, I'm just going to join these together, and you can simply select one, select the other, Control J, and now I have one mesh. So our scene is set up. First thing I want you to do, and this is really, really important, save. This might seem weird to just throw this into a tutorial, but save your file. You're working in an experimental build from potentially months ago. Things might break, things might crash. I'm going to head over to geometry nodes here. And I'm going to just adjust my viewport here. I don't really need the spreadsheet for today's tutorial. It's quite good for inspecting stuff, but maybe not for today. And I will need to just make sure I have a panel open here as a timeline. So we can see this is all the animation data from the armature. So I'm just going to make sure I've selected off this. Collapse both sides of this, and you can press home if you want to just snap that to the view. Now, our timeline is probably too short, 250 frames. If I actually do just select my armature, then I can see that I have keyframes as late as 6:35. So I'll just extend my timeline to match. And there we go. So 635 frames is what I will be working with today. We're all set up in Blender now, ready to start working with our animated character. And there's a few things that I want to be able to kind of teach you along the way here, just to make sure that this is a fruitful session for you. The first thing is actually not something that we need in this situation, but it's something that if you're following this kind of tutorial, you might be looking for. So if you are working with a deforming mesh, so in this case we have sort of rigid skinning, whereas you might be actually dealing with something which is deforming and changing surface area. So let me give you an example of this. And I'll also show you how to fix it. So let's come into our geometry nodes. If I go and distribute points on the faces, and I tab into edit mode and I start moving points around, so essentially deforming the mesh, you can see as I do so, we recalculate the points. This might not be what you want, because you might be wanting continuity between frames if you're doing something like a plexus effect where you have points that are joined together, or if you have hairs flowing on the surface, you might not want those points to be recalculated as the surface deforms. What can we do about pinning points to the surface? Well, if you have an animated deforming object, what you can do, if I just temporarily pause this geometry nodes, is you can duplicate that object. And on this second one, if it's based on an armature, you can remove the armature. If it's something like an Alembic cache, you can remove that. So essentially what you're doing is you're creating a static copy of your mesh. Then you can drag this into your geometry nodes tree. I'm actually going to go ahead and hide this. So I always keep a collection called hidden that is just disabled in my scene, excluded here. Go back to my plane object here. So let's turn back on our geometry nodes. If I move this, we're still getting that movement. However, if I actually distribute points on my other plane, well, now you can see when I deform the input plane, nothing happens because it's not doing anything. So what we now need to do is we need to transfer the positions from the surface where these points are. This is actually very simple in 3.4 and above. We can use the sample UV surface. So go to mesh, sample UV surface. We're going to be sampling our input mesh. We're sampling a vector. This is going to be the position. And the source UV map is just the UV map that exists. So another thing that you need to have is a UV map that is the same on your static version as well as your animated version. And we're going to use this essentially as a dictionary to look up from one to the other what the position should be. Input, named attribute. Now this is the same mesh on both sides, so it's just going to be the UV map for both. So there and there. And then we can set the position to this value. So use a geometry set position like so. And now, as I move this around, you can see that we're not recalculating those points at all. So this is how you would work with creating points on a deforming mesh, because now things are stuck to the UV map. So this is kind of an aside from our tutorial, but I do want to just include that because if you're going to be working with character data, if you have this animation retargeted onto a deforming mesh, then you might want to be able to pin your points to that mesh. Now in our case, what we're going to be doing is something a little bit different. So this is where the fun comes in. We start working with simulations. Grab your Rokoko base model here, the Newton base model, and we're going to add a new geometry nodes graph. So this modifier is going to be after the armature modifier. In our geometry nodes, go ahead and add a simulation output. So let's add this first. And then we also want to add a simulation input. These two now get joined together. So at the end of the last tutorial that I did on simulation nodes, we had a look at how we could inject animation data from a previous simulation into subsequent simulations. And this is something that will make itself apparent quite quickly. So as I play the animation, just straight through here, this is going to give us the animation data from the input to the output, just like normal. Now, what happens if we go through the simulation? Well, we're going to go into the simulation input, to the simulation output, and to our group output. So now when I press play, nothing comes through. And there's a problem here. And if I go back to the start, then you can see that we've basically loaded the mesh into the simulation, but then the simulation is a closed loop. So we can read it out each current frame, but it's not going to take anything from beforehand. So what we need to do instead is actually ignore our simulation input node. What this is essentially the return point for the loop. And we're going to inject our animation into the middle. So we can do this with a join geometry node. Plug it in like so. So now what happens is our animation data for each frame comes in, joins, returns, and then the next frame will join in. So what we're going to see in this case is each frame of the animation gets added together into our scene. This gets a little bit hectic. So what we want to do is find a way to delete every frame that is older than a certain number of frames. This is our first thing that we need to do here. So to keep this nice and fast and flowing, let's delete everything which is older than 5 frames old. I want you to just take a moment here and pause the video, think about how you would do this. It's not immediately obvious how you might delete old information or how you would think about even finding old information. Pause the video, have a go, because once you work this out, the rest of simulation becomes a lot more straightforward. All Right, so the way that we're going to do this is we're going to store the current frame on our geometry. So Shift A, attribute, store named attribute. We're going to be dropping this onto our input geometry here. We're going to be storing an integer on the point domain. I'm going to call this one current underscore frame. Shift A, we need to be adding an input scene time node, and we are interested in storing the frame of the current mesh. I'm just going to frame up these 3 nodes here, so Control J, F2 to rename. I'm going to call this one input geo. What happens when we store this current frame is that the mesh data has whichever frame it is, frame 1 at the moment. The next frame will be stored with frame 2 and frame 3 and so on. The previous versions do not get their frame updated because it is just values and it's being looped through. What we can then do is we can delete any geometry that has a current frame value less than some values off the current frame, and that will be our difference. So Shift A, geometry, delete geometry. Going to be deleting points, and we need to compare. So we need a less than. We want to know the current frame. So grab an input named attribute node. We are looking for current frame. You should find it in here if you've moved the animation forwards. Otherwise, you can just write it through. This attribute will only exist if you have moved a frame forwards. Before that point, it won't exist because it needs to come through the loop. So I'm going to compare where the current frame is less than the scene time frame, subtract an integer. There we go. So if I set this to 0, then we just have the current frame. If I set it to 1, you can start to see that we're getting a little bit of trailing here. If I set this to 5, then you can see that we get the 5 previous frames. So already we have a pretty fun effect going on here. So far, what you've learned is how to bring an animation into a simulation loop and create this kind of onion skinning effect, almost anyway, like a past frame trailing effect based on the animation data. And you can use this in lots of ways. So for example, you could instance a bunch of models and you could delete all but a specific frame. And this will give you multiple instances of your animation with certain frame offsets. So that might be an interesting way that you can use geometry nodes and simulation nodes when they come to create randomized animation offsets within a group of people. In terms of performance, that is probably not an ideal way of doing it. This will bog down fairly quickly. Even if I set this integer to 10, I'm going to notice, a significant frame drop. Now here's another thing that is important to note with simulation nodes. Simulation nodes are basing their evaluation of the simulation on what Blender sees. It's essentially evaluating the dependency graph. So what this means is if you're used to doing playbacks of things which are a bit slow, you might turn your playback on your timeline from play every frame to frame dropping, and this will make it play at real speed. However, you might also notice that some of our frames are being dropped and then they're not being included in the simulation. So it's important to make sure that you keep your playback to play every frame. It will be slower, but it's important that geometry node sees every frame. So those nodes that we just made there, this is going to be renamed to time mask because we are deleting based on older times. So what's the next part of this? We need to create particles on the surface that get thrown off as the dancer moves. For us to do this, we need to evaluate what the surface velocity is. So we need to know how far has the mesh moved from one frame to the next frame. That's all we're going to be evaluating. So rather than the 5 previous, what I want is just 1. So just the previous frame, but instead of having both the current and the previous frame, I only want the previous frame because what we're going to be passing out at the end here is just one character. So I need to know what the current character is coming through here and how it compares against the last frame. So to set this up, we're going to remove our join geometry. We no longer need this. We're going to be bringing our store attribute through straight to the simulation output. Now we need to actually be storing some information about the surface velocity. So let's go ahead and add an attribute, store named attribute, onto this noodle coming from our input geometry. This one I'm going to be calling pos for position underscore delta, meaning difference. This is going to be a vector and it's going to be stored on the point domain. That is fine. Now what I need to do is I need to compare it against the previous frames. So rather than using less than, this yielded us the current frame and the previous frame. We want to know only not equal. Delete everything where the current frame is not equal to the actual current frame of our animation, subtract 1. And this will give us just the result of the previous frame. So now this delete geometry passes out one version of our character, one step in the past. We can use this through a sample index node. Remember it's the same mesh, right? So they have the same vertex order. We need a geometry sample index. Plug this onto your geometry. We're going to be passing over a vector on the point domain. That is fine. The value is going to be the position and the index is going to be the index. So each point goes to each point. Just going to position these underneath here. Now I just want to work out the delta, so the difference between the previous frame, subtract, and the current. There we go. So let's plug this onto our value and then we can have a look at what this looks like. So make sure you're saving. I'm going to come after my simulation output here. I'm going to grab an input named attribute, copy my position delta name in here. This is a vector, and I'm just going to use the default viewer. So Control Shift left click on both of these. Make sure you have viewport overlays on and you will get this sort of effect. What we're seeing is the vector that is the difference between the current position and the previous frame. Looks kind of disco. Sometimes it's going black. This just means that the vector is negative. It's pointing into the negative XYZ space when it is black. We can visualize this a little bit easier, actually, if we use, for example, an extrude node. So let's put on a mesh, extrude mesh. Let's just get rid of our viewer node here. I'm going to be extruding vertices, and I'm going to be extruding the offset from here. There we go. That's interesting. So now we see it has this sort of trailing edge behind the motion. In our case, we actually want that trailing edge to be pointing in the direction the motion is going. So we're not interested in back where we've come from, we're interested in forwards where we're going. To do this, simply change the order of your subtract node, select it, Alt-S will switch sockets, and now you can see that those lines extend in front of the motion as the character moves around. So now we have everything that we need to be able to start our proper simulation, and we're going to do this in another loop of the simulation. So pause that animation. I'm going to actually delete this extrude and named attribute. I don't need those. What I want is to distribute points on the faces. Now, if you're working directly like I did, just with that FBX straight out of Rokoko, then you will actually notice that this is, it's got a little bit of a different scale to what we would be used to in this world. And there are ways to square out your scale properly, but in this case, I just imported it by default, and we're just going to work on the assumption that we use less density. So drop your density down to about 0.4, 0.2, something like that. So quite low. And I'm also going to just set my point radius to be a little bit higher so that we can see them properly. There we go. So all still good. Let's go ahead and start a new simulation. Shift A, we're going to add a simulation output followed by a simulation input. These two are now joined together. Connect your geometry to your geometry, and just like before, we need to be injecting our mesh into the middle, or our points into the middle, because otherwise we're going to lose the compute from before. So use a join geometry, just like this, and view the output there. Once again, same problem. We are just filling our scene with points as we paint the character every frame into the world. It does look kind of beautiful though, doesn't it? But it gets very slow. So what we need to do actually here is a little bit of culling. We need to deal with the lifetime of your particles. So we're actually going to be doing pretty much the same thing as we did before with our time mask. So go ahead and just select this, duplicate it and bring it up. And I'm going to move my second loop just up nice and high. I'm going to give myself a lot of space for this section. So this time mask, I'm actually going to rename to lifetime because this time that we're using it is more similar to when you're using a particle system and you set the lifetime of particles. Now we're going to change our not equal to less than or equal. We're going to add a geometry delete geometry. And we're just going to plug this on here. So now as I play, you can see that we have not very much going on. If I set my integer something a bit higher, maybe 20, then you can see that we have the same effect that we had before. We're deleting points as they become a certain age. It's a little bit too consistent. So what I want to do in this case is actually randomize this integer. So delete that integer, and I'm going to add a random value. I'm going to set this to integer, plug this into my subtract here, and let's randomly delete between 50 and 100. Maybe I could go a little bit less actually. Let's go maybe 10 to 30. There we go. That's giving us a little bit of sort of dithering towards the end. I might actually turn down the density of my points as well. Something like this, just to give myself something a little bit easier to work with. All right. So far, so good. Now you will notice actually when I get to the end of an animation and it loops, the trailing effect will just cancel and restart. This is kind of a limitation of simulation nodes. It makes it very difficult to do loops properly. If a looped animation is something that you're looking to do, what you would want is essentially to create your animation strip, do this in the NLA, and you can stash it. You can do another one with a frame offset, and then you can blend between them so that you have something which will loop back into itself naturally. Power of the NLA. And then what you can do is you can essentially pre-roll your animation to give yourself time for that animation to start, for the simulation to start. And then afterwards, you will just cut off those frames at the beginning to leave you with that perfect loop between the exact same points in those two tracks of animation with the blend in between. So that's a nice way to give yourself a perfect looped animation where you can pre-roll the simulation so that in the final video, it appears to be properly looped. So we've dealt with our lifetime. The next thing I want to do here is make these move. We have, if I add a named attribute, we have our position delta underscore delta. This is our vector, and this exists on all of our points. If I view this, we can see the vector that is on each one of these points. We want to make sure that this is being added to the position. So we're essentially going to offset each frame by some amount of our position delta. It's fairly straightforward to do this. We're essentially turning this vector into motion. So we need the scene time. We need another named attribute node, which we're going to bring in the current frame. So we now have the frame, like the scene frame, as well as the frame of the particles. This one is an integer. If you take the current frame and subtract the current frame attribute, then what's going to happen here is we now have the value of the age of the point in frames. So I want to then convert this to seconds because we're going to be dealing with meters per second when we're actually running our simulation here. So we can start using actual, useful values that you might be aware of. Things like gravitational constant being 9.81. We can use that if we're working in seconds. So we just need to convert our frames here to seconds by dividing by, in this case, 24. So add another math node, divide by 24. and then we are getting the frames per, meaning divide, second. Go ahead and frame up these 4 nodes here, Control J, and I'm going to call this one age. So this is the age of each point. If I view this as we play, you can see that the newest ones on the front of the motion are black because they are new, and the oldest ones are going to be somewhere between 10 and 30, so somewhere between half a second and 1 second old. And that looks about right. So again, I'm going to pause that. What we can do is take our position delta and we can simply scale it by the time. So add a vector math, set to scale. We are going to scale our position delta by the age, and we're going to use this as an offset. Geometry set position offset in here. So I'm going to go back to the beginning, and you're going to basically see these points are now being thrown off. And actually, if I make the lifetime a bunch older, then you can see that they just get thrown off and they keep going in the direction that they were born in. But this really just leaves a mess. So we need to work on this a little bit. For example, we might want to add gravity to our points. We might want them to, come down to the ground. You might want to make them add noise to their positions so that they can sort of fade out and become misty. So you have loads of options when you start getting into this kind of territory with simulation. You can have a lot of fun with it. What I'm going to do is I'm going to add gravity. So rather than this whiteout that we're seeing, what I want to do here instead is mix towards vertically down based on the age of the particle. Now, this isn't physically accurate, but what I'm essentially doing here is I'm visually cheating it to look like I'm factoring in things like wind resistance that would naturally slow down motion as we add vertical motion. It'll make sense when we do it. I basically just don't want to get into loads of coefficient calculations. At this point, we can just mix towards a vertical vector. So let's add a mix node. This is under utilities, mix. We want a mix vector. So we're going to put our position delta into socket A, and we're going to add another vector here, which I'm going to make sure I rename to gravity. So geometry nodes and Blender is going to be working on Z-up coordinates. However, a lot of animation data, and indeed Rokoko, they are working on Y-up coordinates. So actually, if I add -9 to my animation data, you can see it falls this direction, which is quite an interesting effect. The point is we want to be falling vertically downwards, which is in this case actually going to be -9.81 in the y-axis instead. So now you can see it falls vertically. And that looks about right. -9.81 kind of feels like real world gravity. So that's what I'm going to go with here. It falls in a very satisfying way. If you're not a fan of these stretches between here, then what you might want to do is go back to your Rokoko Studio and on your export settings, increase the frame rate of your export to something higher. So if you want that animation to be smoother, you can just simply work with more frames. I'm going to keep mine to 24 FPS for now. But yeah, that is how you would resolve this a little bit higher. So right now it's falling down completely. If I set my factor on the mix to 0, then everything moves just in the direction that the surface was at the point that that point existed. So we can work with a map range node coming off the age. So take a map range. Apologize for my node organization here. I know I keep moving things. So we're taking this map range. This is going to be giving us the age of this. I'm going to go from maybe 0 to 2. We will go from 0 to 1. So as these reach 2 seconds old, they will move completely towards a vertical descent. Now we can actually reduce the amount that we go, so we never quite reach 0. So these will always throw off slightly in the direction. You see these throw off quite nicely there. See that first one actually, this is something to be aware of. This first one is going to pop up like this. because the previous frame to the next frame generally is quite small, but for that first one, the previous to the current is going to be from 0 to the current position because there was no previous frame. So that's why it basically just scales up and it's a very high value. We can actually remove this glitch frame, so apologies, I know I'm dancing around. Let's just make sure that we've cleaned up after ourselves. Add a delete geometry after our distribute points on faces. We are going to be deleting the geometry where the current frame attribute input named attribute of the current frame is equal to some value. And in this case, I think it's probably going to be 1. So if I go back to the beginning and start it, there we go. And if I make sure that's playing through from the end, there we go, we didn't get it. So every time we start fresh, you will get 1. But when it naturally restarts, because we actually delete that first frame there. All right, I really love this. Kind of looks like sand just falling off her. Let's frame up those 3 nodes there. Let's just call this one glitch. And go back to our main loop above. These 5 nodes that we just made, the named attribute mixing towards our gravitational constant, scaling based on the age of the particle. These nodes, I'm just going to call these ones velocity, because this is basically dealing with where our points move to. But we have some more work to do here. We're not done with our motion. The next thing we want to do here is add a floor. Right now everything falls infinitely until its lifetime runs out. However, wouldn't it be nicer if things hit the floor? And I want 2 things to happen. I want their Z position to stop going down, and I also want the spread to slow down, as if it's hit a surface with friction. Now, we can go into actually colliding with other objects and how we would deal with that, but perhaps in a future video. For this one, we're just going to do this with a kind of a mathematical plane. We're just going to use the Z equals 0 position as a stopper for vertical movement, and then a multiplier to reduce the amount towards 0 for horizontal movement, just to make sure it feels like friction. So again, this is all smoke and mirrors. We're not doing proper calculations here, but it looks pretty good, so I'll go with that. What I need to know is the current actual position of the points. So to do this, I need to know what the position add this scale value is. So why am I doing an add here? Well, when you plug into the offset of a set position node, you are doing a position add vector. So doing this gives us the explicit position of the points at any moment. What I can then do with this, in fact, let me just say current position, just to make sure that we're keeping track of this. If I separate X, Y, Z, then I can use the Y axis. Remember that we're dealing with Y in this animation because it has a transform on it. So we're dealing with the Y axis. I know it's confusing, but just go with it for now. When the Y axis is less than or equal to 0, this means that we have hit the floor. And in that case, what I want to do is I want to stop offsetting in the Y axis. So I need another separate X, Y, Z coming off our scale here. And I'm actually just going to join this one straight through to a combine X, Y, Z. And I'm going to join my X and my Y and my Z. So we haven't really done anything, but we have exposed each axis of our animation offset. So when we go below that Y equals 0, so less than or equal to, we want to switch our Y offset. So let's use a utility switch node, set this to float. I'm going to drop this on Y. When this is true, we're going to switch to having 0 offset. So if we play this now, then we're going to get this where it hits the floor. However, the floor is where the origin of the mesh is, and we can see that there's a bit of an issue. Our origin is not on the world origin. Let's just make sure that our object is selected. Here we go. And then right click, set origin to 3D cursor. Now everything's going to move down to begin with, but when we continue the animation, we can see that mesh, because it was bound to the armature, it's actually going to work fine. So let's reset our animation. Now we can see all of these points just go straight down and hit the ground. However, no friction. So everything just hits the ground and it keeps flowing out away from our character. So we also want to do some controls here on our remaining axes, the X and the Z. Let's put on a multiply. So we want to multiply these towards 0, or essentially mix them towards 0. But it's a bit cheaper to do a multiply here than an interpolation. That is what a mix does. We're going to take our current position, this y-axis, through a map range. And we're going to use this to fake our friction. So remember, this separate XYZ here on our current position, this is calculating data coming down below. This is not being stopped by the ground. So what we can do is we can say, okay, well, when it hits 0, stop moving it down. And this is why it's now moving outwards. And in the space where it would come from here to maybe 2 meters down or something like that, in this space, we can use this to multiply our horizontal movement towards 0. So let's do this and it will make a bit more sense, I think. On our map range, let's set this to be from 0 to, let's say, -5. So we're going 5 meters down. And then we're going to be multiplying from 1, which is our current offset per frame, which is going to give us that smooth movement outwards, towards 0. So when the particle goes below -5, its adjusted version is going to have slowed down to 0 and have a z-axis, or sorry, a y-axis position of 0. Hopefully I'm not talking in circles here. Hopefully this makes sense still. Let's just try this out and see how it looks. So let's restart our animation. See things hit the ground now. And then they stop. So it looks like there's been some friction on the surface that they've come into contact with, and that has made them stop. Maybe instead of linear, let's go with smoother step. Let's see how that looks. Maybe that's okay. And there's other ways that you can make this more accurate as well. So for example, instead of using the distance below the z-axis, you might want to have a way of calculating the time that it has passed that z-axis, and you might want to add additional attributes to be able to compute that. So what we've done is essentially worked out the friction on the surface, stopped it from going below the surface, and it's just given us a nice effect. I might increase this down to something like -8, just to make that surface feel a little bit smoother there. I'm going to make these a little bit more condensed, and we're going to frame these up like so, including our current position actually, Control J. Let's call this one floor. So now we have points hit the floor and behave correctly. Here's another thing you might want to do. Rather than every point, every frame being created and dropped on the floor like she's just made of sand, what we may want to do is create something like an escape velocity. So if you're doing a simulation where your character is made of a liquid or paint, something like this, then you might want it to be that only when they move at a certain speed does the matter leave the surface. And this is actually very simple to do. We just need to delete points where the magnitude of that position delta that we originally calculated, that surface delta, where the magnitude of that is below a certain amount. So let's just pause this, make sure you're saving. We're going to grab a geometry, delete geometry onto this noodle. We've got our points here. We're going to be deleting any point which is less than, and this is going to be a float. Let's bring in our named attribute next. So input named attribute. This one is going to be our pos delta, which is a vector. And we need to find the magnitude of that, so the size of that vector. When the delta between 2 points, when the length of that difference, the distance that it's traveled, when that length is less than something, then it means that it's going slower. So if we find the length with a vector math node, coming into that compare. So if it's less than 0, then that means it hasn't moved. So with a threshold this low, we're not deleting any points. So if we increase this to maybe 10, well, now we only get points coming off when she moves extremely quickly, when there's big hand movements happening. So this is not meters per second. This is meters per frame. But also remember that we have that transform issue where it is scaled. This is actually 100 times off. So these values might not be real world values. You can have a lot of fun with this. For example, setting this to something around 3, I found was a little bit better. You didn't get all of the points, but you still got a significant amount. But like the body stayed fairly consistent unless there was a big movement. All right, let's frame and rename. I'm going to call this one escape velocity. And I'm going to pause and I'm going to save. Keep saving your work here. Let's add one last thing to this setup, and that is going to be color. For our sakes, we're just going to preview the color because I wasn't able to get rendering working, unfortunately, with this slightly older build. But hopefully by the time you're watching this, there might be a new build of 3.5 or 6, and you might even be watching it after 3.6 is released, in which case you will have a completely stable version. Let's come in here. We are going to be setting the point radius. I'm going to use a random value. And I'm going to set this to be between, I don't know, 0.5 and 2 maybe, in my case. Your mileage may vary, so do just work with what you need. Just gives a nice bit of variation. And then I'm also going to add some color. So you'll want to store named attribute. In this case, what I'm going to do is I'm going to base it on the current frame value. And I'm just going to do this noise based. So Shift A, we're going to use a named attribute. So input named attribute. We're looking for the current frame. Let's put this just through a noise texture. I want noise, not white noise, because noise is Perlin noise. So you have a nice gradual continuous change between randomness. However, a white noise, it'll appear to change too drastically between frames because it is completely disconnected based on input value. So in this case, we'll use a noise texture, and we can then set the smoothness of the transition by that scale. I'm going to go through the color here. Let's plug this up into our store named attribute. And this is something interesting, probably a bug. If you put this through an RGB curves, simulation nodes will kind of glitch and not really enjoy it. I found that my viewer node was not working when using an RGB curve. So probably something I should report, but just for now, we're going to be just using a map range to set the contrast instead. Let's store this one as color on the points. And I'm going to use a named attribute node immediately just to view it. Yeah, so I'm going to view this like so. So we can see this is changing quite drastically, quite quickly. Let's reduce our detail right down. Let's reduce our scale to maybe 0.1. Now you can see that we're getting a little bit slower. Let's go even lower here. So now we get a nice gradual change. I'm going to increase that contrast with a map range node, set to vector, and I'm going to increase from point to 0.2 and 0.8 as my input values to be 0 and 1. And that's essentially increasing the contrast of this color. Now, because this is based on the current frame, all of the points as they're created maintain their color. And this can lead on to some other fun effects. So you can do things like dynamic paint, where the surface color or the point color is transferred onto some mesh and stored based on proximity or something like that, right? Sample nearest within a certain radius. So then you can do dynamic paint based on the color of your model at any moment in time. Another great thing if you're using Rokoko and simulation nodes like this, because it is just reading the depth graph, and Rokoko, if you have a suit, then you can do live streaming directly into Blender. So you could dance live, or you could have actors performing live and have live simulation. So this might be an interesting way for you to do some kind of live experiences, things like this. So I hope you've enjoyed this session. I know we've covered quite a lot of stuff, and geometry nodes and simulation nodes, they're not yet out. So we are using the experimental branch for today's tutorial. However, we are expecting simulation nodes to be in master for 3.6 and beyond. So the shape of it, what you're learning now, should be true. And the key takeaways here are going to be store named attribute, store named attribute, named attribute. This is how you pass data back and forwards between itself and its previous states. And when using animation data, you must always inject your animation into the middle of a simulation. Blender has just crashed, so thank you. This is the end. I hope you've learned something, hope you've had fun, and I'll catch you in the next one.